Welcome to the session. That's we'll have 5 presentations before lunchtime. So the first speaker will be Juana David, and he will please, Juana, the floor is yours. I think you can share, no?
Yes, good morning, everybody. Thank you very much for the introduction. I will share my, yeah, you can see this. So I will speak today what are the development steps when we want to make a membrane and we start from material. Yes.
We cannot see your screen, huh? Yet.
Okay, sorry.
Could you share?
Now you can see it? You can see my screen?
I just put you, now yes.
Yeah, okay.
I put you in the first screen, so that's fine, okay.
Okay, so you can see my screen now?
Yes, yes.
Okay, thank you very much. So I will speak about membrane development steps, how we go from material to a final product. I work in Tecnalia, which is a non-profit research center situated in the north of Spain, in Basque Country. So if you look at a few examples on the European map, we are similar to CAA in France, Fraunhofer in Germany, or TNO in the Netherlands. And we are about 1,500 people of different nationalities, and about 250 of us have their PhD. What is important in numbers is that almost half of our financing is private, is coming from private research projects. And from the remaining half, about 33.2% is coming from competitive public projects. And only 19.7% is direct funding from the state. So we are big. We are divided in 6 business divisions: in building technologies, in energy and environment, ICT, industry and transport, health, and lab services. I am part of the membrane group, membrane technology and process intensification research group. We mostly work with polymeric membrane, with gas separation membrane, and these are polymeric and mixed matrix membrane, carbon molecular sieve, and palladium membranes. And we are focused on applications like carbon dioxide capture in pre- and post-combustion processes, biogas upgrading, natural gas upgrading, and hydrogen production, mostly with palladium membrane, where we integrate them also in membrane reactors. So the outlook of this presentation: first, I will give a very short introduction to membrane processes. Then I will speak about the membrane structure and geometry, and what is the development strategy that we do when we make a new membrane. And I will give some examples of Tecnalia developments. So here I like just to classify very briefly the membranes according to the nominal pore diameter. So we have 2 domains: liquid permeation and gas permeation. And we have 2 types of membranes, like with from 1 to 5 angstrom pore diameter. These membranes are all dense. Basically, this distance is, if we speak about polymeric membranes, is the interpolymeric chain distances. And from 20 angstrom onwards, all membranes are porous. If we look at liquid filtration, we have ultrafiltration and microfiltration. And if we look at gas separation, we have some kind of Knudsen flow membranes, which are not very selective, but have high fluxes. And then all polymer membranes separate gases. That separate gases are dense. And in between 5 to 20 angstrom, we have intermediate domain. The membranes are neither dense nor porous. And from the gas separation point of view, this is highly interesting domain because here the membranes are able to separate according to the size of the gases. So they have a sieving mechanism. And there are different types of materials that can do that. It can be carbon-based, ceramic-based, or mixed, like a hybrid between metal and organic molecules, which are metallic organic framework. So if we look at the membrane structure and geometry, here is like an overall classification. A membrane can be also a homogeneous dense film that is done by solution film casting, but this kind of membrane is not found in a practical application. It is used to determine the intrinsic properties of a given material or polymer. For all commercial membranes are symmetric, and this is because the flux through a membrane is inversely proportional with the membrane thickness. And then the membrane itself is the top layer, which is as thin as possible. And because it cannot be self-standing, it's supported on a porous sublayer. So if the top layer and the porous support are made from the same material, then they are defined as monolithic membranes and are done by phase inversion in a single-step process. And this is highly desired because it's very simple. And in contrast, when the material cannot be made by phase inversion into a membrane, it has to be coated on a support that was previously made, either by deep coated or it has to be synthesized in situ by interfacial polymerization. So composite structure, it's also asymmetric. It's composite because it's done from two different materials. And the manufacturing process, it's a bit more complicated. Normally, the composite membranes so far are flat sheet, but they can also be hollow tubes as geometry. So here there is an example of thin film composite membranes. These are based on a polyactive membrane material, and they are commercially today at pilot scale. This is a very good material for carbon dioxide separation from nitrogen. And I want to highlight the very complex structure that a composite thin film material or membrane is needed to have. So first of all, we have the support, as I said before. We have the membrane layer. And in between, there is an intermediate layer, which is called the gutter layer. It's made out of a highly permeable polydimethyl siloxane normally. And it has two main roles. One of them is to act as a gas collector for the gas flow to enter easily into the pores of the sublayer. So if this membrane layer would be directly on top of the pores, then the only active area of the membrane would be the one that's situated just above the pores. So we need this gutter layer to act as a gas collector. Then the other objective is it makes a much smoother surface. So therefore the selective layer can be very thin, and it has about 100 nanometer thickness, a commercial layer. And then it can be an extra layer, which is a protective coating layer. So to make this kind of architecture, it's a multi-step process and can be quite complicated. Then here I show an example of a monolithic asymmetric membrane in the geometry of a hollow fiber. So here the outer diameter is about maximum 500 micrometers. And you can see the top selective layer, it's on the outside, and there is a smooth transition from a dense top layer to the porous sublayer, and everything is made from the same material. So when it's possible, this kind of geometry and structure is desired, but not all polymers can be processed this way. So here I show an example, like a picture of hollow fiber membranes. And I would like to explain why we prefer hollow fibers. So first of all, in order for these fibers to work as a membrane, we have to put them in a module with resin, with epoxy resin, like the blue color here. We are able to separate one side of the membrane to the other in order to create a feed side and a permeate side. And then this geometry is preferred because of how much membrane area can be packed in a module, in a tube. So if the fibers, so starting from a diameter lower than 0.5 millimeters for the outer diameter of the fiber, there is an exponential increase in how much area can be packed in a unit volume. And this is why the hollow fiber geometry is preferred in respect to the planar one that cannot be packed so densely. And what is very important also is process design and membrane system components. So here I give an example for natural gas treatment. It's not separated in one single unit. There is a second unit that recirculates the permeate from the first unit in order to have a very low methane loss for the whole project, whole separation. And then what is also important is the pretreatment of the gases. We do not want to have streams that reach the membranes, streams that contain particles, water droplets, heavy hydrocarbons, or other heavy impurities. So therefore, when we make a membrane development strategy, we first start with process analysis and optimization. So looking at the process, at the application where we want to use the membranes, we define the target values for the membranes in terms of permeability and selectivity. Then we develop the membrane with the asymmetric structure and hollow fiber geometry, preferably as I described before. And we test the membrane, we scale up them, we try to reach a commercial membrane. So as I said, we start with a target performance. We either select a material based on the literature, if there is available material, or we develop one, like in the Biopolymers project I was saying. Then, first of all, we do homogeneous dense film membranes in order to determine the intrinsic separation properties of these materials. If we like them, then we start doing an asymmetric hollow fiber membrane. And in order to develop a hollow fiber without defects, we have to do several trials. So we have to optimize the hollow fiber fabrication process. And if we finally have good results, we will see if the recipe is reproducible. If we can scale up, we test a prototype level. So I would like now to give some examples, and I focus on post-combustion carbon dioxide capture. So here, DMT will later explain what are the industrial requirements. So this is in session 2B at 3 p.m. But I will just briefly say that we have an inlet gas that contains up to 20% of carbon dioxide. And what is challenging is that it's coming at low atmospheric pressure and that it has very high flow. So compressing such a high amount of stream is very expensive. Therefore, in order to be competitive with amine, we need membranes that are highly permeable, about 2025 GPUs, that would have a carbon dioxide nitrogen selectivity higher than 30. So here I listed a few materials. In the upper part, we have all this P-bar type chemistry, like polyether block amide chemistry, and polyactive. It's also a block copolymer. So these ones are, so far, they cannot be spun into monolithic hollow fibers. and some of them, they have good carbon dioxide nitrogen selectivity, and this is intrinsic permeability in bar, so they can be transformed into commercial membranes by deep coating or porous supports.
5 minutes, Oana, 5 minutes.
Okay, I will finish soon. And on the bottom part, they are all the materials that can be spun directly into monolithic hollow fiber membranes. So I will give an example with P84. Has a low permeability of carbon dioxide, but the selectivity is good. So if we manage to make a very thin top layer, the permeance will be higher. And then I will speak about 6-FDA DAM, which is very permeable, but the selectivity is lower, so we try to increase the selectivity. And then I will show a bit how we change the chemistry in P-Bax type polymers. So with P84, we managed to do hollow fiber membrane with a very thin skin without any defects, about 56 nanometers. And we didn't need to do any post-treatment in order to seal any defect because there were none. We managed to scale up the process, but the permeance was 33 GPU, so it's much lower than the objective for post-combustion carbon dioxide capture. And then with the 6-FDA DAM, the polymer I showed you that was much higher permeable, we try to increase the selectivity for this separation by incorporating an inorganic filler that can sieve between carbon dioxide and nitrogen. And this was ZIF 94. It's a metallic organic formwork. So that could give good sieving properties. And here on the SAM picture on the right side, you can see the particles, which are nano size, embedded inside the polymeric matrix. And with this experiment, we managed to increase carbon dioxide permeability a lot, but the selectivity was maintained constant. So we didn't manage to increase also the selectivity. And now I'm coming to Biopolymers project. So this is the chemical structure of a polyether block amide type polymer. Has already good gas separation properties for post-combustion carbon dioxide separation. But the main disadvantage is that it has to be processed by coating and make all this composite structure. So in Biopolymers, on one side, we will make deep hollow fiber membranes by deep coating, and on the other side, we will change the chemistry of polyamide and of polyamide and polyether block in order to make them spinnable into monolithic hollow fiber membranes. And here, the starting point will be a new PBA type polymer that has that is made from here we have polyamide 11 in this bio-PBA that is from bio-based building block and has higher. It has very good gas permeation properties, much better than any of the polymers studied so far. So this is a new polymer from Arkema. Okay, thank you very much for your attention. If you have any questions?
We have time at least for 1 or 2 questions. Just raise the hand or send the question by the chat, I think. You have to send by the chat.
I'm looking at the questions now. So from Professor Fausto Carlucci, what is the benefit in terms of cost when using biopolymers? We will have to see. I hope there is a benefit, or at least the cost. The idea is not to have it more expensive, obviously. Yeah, we have this life cycle analysis and everything in the project. So there might be no benefit.
I guess one is to use because it's coming from oils waste. Also, in the biopolymers is coming from recycling waste products. I think no oils or whatever. Which type of
polyamide 11. It's coming from castor oil, and it's like in the chemical industry. It's not it's since long time being used.
There's okay one.
So LCA might say that it's good in terms of environment, but not cost.
Okay, yeah, yes, you have life cycle cost analysis, I guess, also in the yes. Okay, there's one question. The last question with Ina Kim is: do you need an elevated pressure for the feed gas for post-combustion CO2 capture?
In general, for any kind of separation with membranes, it's good to have a high pressure at the feed side is better. But in this case, to increase much the pressure of such a high amount of gas stream, it's very expensive. So people are trying to develop membranes that are much higher permeable to compensate for that. So if a membrane is more permeable, then you don't need to increase the pressure so much.
Okay, let's thank you, Anna.
Thank you.
Yes, I think they can contact you later on as well. So let's move to the next presentation. I think it's Vincenzo. No, I'm going to give the first Juana. You have okay, Vincenzo. You have the.
Can you see my screen now, Jose Luis?
Yes.
Is the one with the PowerPoint presentation, I hope.
Yes, but now I see you, not the screen.
Oh.
No, maybe I have to let's do one thing. I will undo this. Let's wait. No, it's fine. Now put your screen again. I think yes, it's fine like this. I don't have to put you in the first position.
Okay, so so you can confirm that you can see my presentation in the presentation mode.
Yes.
Okay, thanks. Thank you to everyone, and thanks for organizing this interesting workshop. The presentation I'm going to do today is on system simulation for integration of CO2 capture technology into steelworks and CCUS clusters. So this is a presentation which has been prepared by me and our colleague from UCL, Sergei Martinov, Richard Porter, and Arun Magerte. A very what happened? Okay, a very short introduction on the project was already done by our coordinator Arun from UCL. So this is part of the C4U project on advanced carbon capture for steel industry integrated in CCUS cluster. It's 22 partners. It's a relatively young project because we start less than 1 year ago. But we are still doing already quite a lot of activity since we are moving to TRL 7 demonstration from the capture, plus a lot of technical and societal studies. So the general objective of the C4U project mostly relates to two promising CO2 gas solid based capture technology that will be elevated from TRL 5 to TRL 7, and this will be obviously studied in terms of optimal integration and techno-economic analysis. As a comprehensive project, we will obviously focus also the economic, environmental, and business impact of the integration of these two technology to processes into the North Sea industry cluster. You can see that, let me just take the pointer, which is here. Where is the pointer? Okay, I think probably you can see anyway in this way. So it's the steelwork plant, which is located here in the North Sea port, and this will be integrated in terms of CO2 quality, pipeline transportation and storage infrastructure, and finally there is the develop and test the approach with stakeholder and user and assess the advanced societal readiness for CUS in industrial cluster. So the project includes different activity, as was already mentioned. So in the first work package 1 and 2 will be the testing and demonstration of the technology, and this will be up to TRL 7 for both the displace and the CASO project. We will have then the integration of CO2 capture in industrial installation. So this will include not only the techno-economics of the process within the steel plant, but also the integration of the wall technology within the industrial cluster. And finally, there will be 2 more work packages, plus the one on dissemination and communication and public engagement, which will assess the quality of this technology, the quality of the CCUS cluster within public acceptance and obviously business model. Now, my presentation is mostly focusing on work package 3 and work package 4, while other work packages are covered by other presenter. So what I'm going to do in this presentation is that I'm going to introduce how these 2 processes can be integrated in a steel mill. I will tell you, I will present the main results on benchmark processes that have been already performed and their techno-economic performance. And I will also introduce the C4U in technology integrated in an industrial cluster, in particular challenge and opportunity. Finally, I will derive some conclusion. So the first activity is the one on work package 3. This is mostly related on CO2 capture technology. The work package is led by Politecnico of Milano, and together with Polimi, there is Manchester University, research center like CSIC and TNO, and industrial partner like Wood and ArcelorMittal. So when you think about an integrated steelwork, you can imagine that it's a very complex plant. So there is a lot of energy stream and a lot of process that are overall integrated. Now, from all these units, you can also identify several CO2 sources, and in particular, the one that is generating a large CO2 emission is mostly coming from blast furnace, although there are coke oven gas, basic oxygen furnace, and the sinter plant, which are also responsible of high CO2 emission. In our C4U project, we will mostly focus on the CO2 emissions which are currently generated from power station and from the use of different gases within the plant. So how we will do that? Basically, we are studying 2 different technology. The first one is the displace technology, and this will apply to the reheating processes. And the second technology is called the CASO process, and this is mostly applied to the blast furnace gas. Now, I don't want to ruin the surprise and the interest on the description of this technology. Therefore, I will kindly invite you to attend a session tomorrow by Paul Cobden and Carlos Albanades, which will go more into the detail of this technology, and they will tell you much more on how this technology are going to be scaled up to TRL 7. So let's assume that these 2 technologies exist, will work, and will be demonstrated at TRL 7. If we imagine our steel plant, we will have, as I said before, different streams that are needed to generate and to produce the steel. So we can imagine our C4U CASO technology integrated using BFG. This will produce a stream of hydrogen and nitrogen that can have different uses, from power generation to hydrogen related products. And we will concentrate CO2 up to 65%, which will go later into a CO2 conditioning unit where nitrogen and CO2 will be separated. At the same time, using the anoxifier reheating oven, we aim to produce a CO2 water nitrogen rich flue gas, and this system will be then converted and purified in the C4U displace technology, where again, pure CO2 with higher purity will be generated, and nitrogen and oxygen will be separated from the stream. Doing so, we aim to reach the combination of the two technology can cover up to 90% the total emission from the steel plant, which is the ambition of this 4-year project. Now, in this work package, we obviously have different activity over the project lifetime, which goes from the definition of the reference technology up to the overall optimal integration of the technology within the integrated steel plant and comparison with main key performance indicator with the benchmark. What we have done so far has been a study on the methodology, on the reference case definition. So within the task 3.1, which is what I'm going to present in the next few slides, we have basically identified the pre-combustion separation process from blast furnace gas. So this is a MDA solvent-based process where the BFG can be purified from CO2, from which we can get our hydrogen-rich gas. And at the same time, the CO2-rich amine is then regenerated in a desorber column by using a low-pressure steam. You can see here our BFG composition and the main operating condition. What is worth to mention at this stage is that the low-pressure steam at 6 bar is used for regeneration. CO2 is delivered at 110 bar. And basically for the base case, which is the one with the mild capture, we are expecting to have a decarbonized fuel, which will have still all CO, very limited quantity of CO2, hydrogen, nitrogen, and other components, including water. There is also a second scheme, which is the one that we call enhanced capture. Now, compared to the previous one, the main difference here is that we also integrate a separation unit with a high temperature water gas shift reactor. This is operated at around 300, inlet temperature of 300, so water gas shift occurs between 300 and 400 degrees Celsius. And while the CO2 capture unit still remain unchanged. What is happening in this case is that we can convert most of the CO into CO2 and hydrogen. This will be up to 67% according to the conditions selected in this process. And then we will have an hydrogen content, which is about 24%. Nitrogen is 62%, and still some water is present in our decarbonized fuel. So we compare those processes in terms of CO2 capture rate of the technology. So this basically only refers to the technology, not to the complete steel mill plant. We have compared also the technology in terms of specific primary energy consumption for CO2 avoidance. So basically, we want to know how much energy is needed to separate 1 kilogram of CO2. We did also an economic assessment. This is referred as levelized cost of the decarbonized fuel and CO2 avoidance cost. And also we defined an additional cost which is required in terms of ton of hot rolled coil when CO2 capture is also applied. Looking at to the performance, so what is worth to mention here is that with respect to the case with no capture, the base case and the enhanced case will have a different overall energy efficiency. This is mostly due to the amount of CO2 that has to be captured, as well as different CO2 specific emission, which becomes much lower in case of the enhanced case. Higher CO2 separation will also result in a higher energy request per kilogram of CO2. And that's what you can see from the spec indicators. In terms of economics, we can see that the hour cost of the decarbonized fuel from the starting cost of 5.2 euro per gigajoule will rise up to 9.7 and 14.8, depending the level of CO2 purification we can achieve. And this also translates in terms of CO2 avoidance, which goes from 40 to 50 euro per ton. These are numbers based on the assumption that we have used and with the BFG composition that is being considered. Moving to the second work package, which is more on the integration of the process within the industrial cluster. In this case, the main objective are mostly related to combine the industrial clusters of North Sea Port, Port of Antwerp, and Port of Rotterdam, which is responsible for 1/3 of CO2 emission from the whole region, which is apparently approximately 60 million tons per year. The idea is to define common CO2 transportation infrastructure and geological storage related to the P18 field, which is located in the North Sea, and they perform the whole economic and safe and environmental NCA of the integrated cluster.
5 minutes.
Yeah, thanks, Jose Luis. I'm almost done. How we will do that? So there will be a first task, which will mostly focus on utilization, storage, and safety. A second cluster, which will mostly look to the logistic and how to operate the CCUS cluster as a whole system, and the life cycle analysis, which will be also applied to the entire cluster. Now, at the moment, as we say, we have just started. The first step is the purification challenge. So, according to the quality specification required from the Northern Light, we have identified already few elements which might become a high challenge for iron and steel industry. This is mostly CO, H2S, oxygen. So if we look into the literature, one of the possible schemes for CO2 treatment requires different separation and conversion step. So we can already notice that after the bulk CO2 removal, there is still a plan that is needed to achieve certain specifications. So this will be highly studied and assessed during the C4U project, mostly because this represents a cost, and therefore it's very important to assess it. Another part which will be studied is also the effect on decompression during the pipeline. So this is important in order to avoid formation of solid CO2 as well as two-phase flow, which might affect the operational and the cost in the transportation part. So moving to conclusion, in this project we have already assessed the benchmark technology. This might lead to 50 euro per ton when achieving a carbon capture efficiency of 83% from blast furnace gas. The second aspect is related to studying both the C4U technologies within the CO2 quality interlinked within two work packages, and the study of this technology and the industrial cluster, which would include 3 large industrial intensive area in the Benelux responsible of 16 million tons per year. Overall, we aim to, at the end, to perform the economic, safe, and environmental SCA analysis for the system. With that, I want to thank you, obviously, the European Commission and all partners for contributing to this presentation, and I'm very happy to take any question if you have some. Thank you.
Thank you, Vincenzo. We have time for 2 or 3 questions. Please write them in the chat. No questions? Let's wait if they have to write. Okay, Vincenzo, do you read the question?
Yeah, I can read it.
Yeah.
So it's a question from Fausto Gallucci. What will be the final TRL of the different technologies? So both technology will achieve a TRL 7 demonstration. There will be more detail in the presentation tomorrow, but I can already anticipate that the 2 technology will be tested in 2 industrial facilities. One in Sweden, in Ljubljana, and the other one will be in Oviedo, close to the ArcelorMittal industrial facility and laboratory.
We have a question for Inna.
Are you considering only ship transport for CO2? Not last minute is for ship transport. Okay, so that's a very good point. If I should miss some information, I would ask to colleague from UCL to complement the answer. I believe so far we are only considering transportation to the, I mean, the one that I'm aware of, it's the transportation which will go to the port. So from the North Sea to the storage part, I'm not sure if this will be transport with ship or there will be a different transportation route. So I'm not able to answer entirely to this question.
Okay, thank you. There's no more questions, I see. So then thank you, Vincenzo. And then let's move to the next speaker.
I think I unshared everything, Jose Luis.
Hi, Marisa, could you share your screen or no? Marija? Yes, now yes. I don't know if you have your microphone. Ah, no, it's fine. Yes, okay. We cannot hear you, Marija, I think. But you have your, I don't know why.
Now?
Yes, now yes.
Right. Thanks.
Thank you, Julian.
Okay. Okay. Thanks. So I can start. Good morning, everybody. My name is Maria Savic, and I'm from Research Institute TNO in the Netherlands. And today I will give a joint presentation.
We're listening you very badly. That's.
I will try to do something. I'm sorry for this. Do you hear it better now?
No. That's... Do you have microphones or?
Yeah, I have a microphone, but something.
No, headphones. I say it's.
No, I don't have headphones with me. Just a moment.
Yeah.
Do you hear me better now? Hello?
Let's see. Start. Use start.
Okay, because I now took my headphones. I hope it will work. Good morning, everybody. My name is Maria Saric from Research Institute TNO in the Netherlands. And today I will have a joint presentation with Anje Plašnikar from the National Institute of Chemistry from Ljubljana. So we are going to talk about use of membrane reactor for methanol synthesis. And this work was done as in the framework of the Converge project, in which we look at the conversion of waste feedstock via gasification to methanol to biodiesel. And here we are developing five nanotechnologies, and the idea is to increase the energy efficiency of the biodiesel production. And here you can see the project partners involved in the project. Do you hear me okay, or how it goes? Sorry.
Yeah, it's okay.
Okay, so the specific goals for this work package are to develop the stable membranes at reaction conditions for methanol synthesis, develop multitubular membrane reactor with the targeted conversion of for feed CO2 and hydrogen of 33% per pass. Typically in the industry we have around 20%. So in this way, we can decrease the recycle, and in this way decrease the reactor size. And we also want to demonstrate this technology and integrated process at TRL5. And partners involved in this work package are TNO and so as we said, we set membrane development targets. And we need to develop the membrane that are stable at operating conditions for methanol synthesis. So temperatures between 170 degrees to 275 and up to 100 bar. We need to have a high selectivity for steam and methanol and high steam and methanol permeability. To do the pre-selection of the membrane, we started with a literature study looking at the different membranes that were tested for steam separation. So what you can see in these figures are let's say, from the literature, typically tested membranes for steam separation to these high temperatures. So you can see typically that they use amorphous membranes, zeolite membranes, or polymeric membranes. And here what is really important is also steam to hydrogen selectivity. So we can see also that in general trend that with the increase of temperature, the PEM selectivity goes down. And this graph also shows some hydrogen to nitrogen selectivity for different polymeric membranes. So we made inventory of the membranes that we will test for this application. So we selected 7 membranes, for which 2 were the amorphous microporous hybrid silica membrane. In TNO, we have a lot of experience with these membranes for evaporation, but we also tested them in the gas separation processes. And we selected 5 types of polymeric membranes. So before I go into the test results of these membranes and characterization of these membranes, I will just give a background of how we produce membranes at TNO. So we produce supportive membranes on tubular ceramic support, and we usually buy these supports from supplier. But these supports are quite coarse, so in order to make a good defect-free membrane layer, we need to apply intermediate supports to decrease these defects. And you can see here in this same picture of the cross-section of the membrane that you have really coarse support, and then we typically apply 1 or 2 intermediate layers before we apply the membrane layer on top. We are using the coating process to do that. And here is just schematic of the coating process with the coat vessel, and then you have a tube that goes with a certain speed through these coating vessels. And here it's actually the picture of this setup. And we can make membranes till 1 meter length. After making of membranes, we typically do the bubble point test to elevate the quality of the support. And based on that, for instance, if you will have certain criteria on quality of membrane, which is here in red, you can see that if you have just support, you don't really have quality, but with the 2 supports, you can reach good quality, and then you can apply the membrane layer on top of it. Okay. So these are the summary of the tests that we did for the Converge project in the separation mode. So we used the feed pressure of 35 bar, which is a limitation of our installation. Permanent pressure was 1.5 bar, and here no sweep was used. This is a composition of the gas that was used, so it's a permanent gases in combination with the methanol steam, which would present typical the equilibrium coming out of the methanol reactor. And what you can see in these figures in the first line, there are water and methanol permanents. And if you look at the membranes, we can see that Lafion in blue crosses, that's black, also the stars, and PI membrane that are green have a higher steam and also methanol permanents. We see also that Betsy membrane performance decreases to 275. But also the Lafion membranes, these are these 2 blue crosses. There are, we didn't test above 225 because we observed that selectivity of these membranes. If you look at the steam to hydrogen selectivity, highest steam to hydrogen selectivity was with AFTES PA membranes, which are yellow squares, and then followed by PI and SPAKE. Based on this, so trade-off between the permanence and perm selectivity, we selected PI membranes as the first preferred candidate, and also BETSE and AFTES PA as fallback options for further testing in the membrane reactor condition. PBMS membrane in Lafion, they were discharging because there was not selectivity at the temperatures higher than 225 degrees. And the SPAKE membrane, although it has higher selectivity, the permanence was 10 times lower compared to PI. And for PBI, we observe both low permanence and low selectivity. If you look at as I said, we selected these 3 membranes for further tests. You can see it here, the comparison of the performance of these membranes. And when you look at the comparison with the literature, here it's in a gray mark, the PI membrane, it has a quite, compares well with the literature. So our project steps is and we are busy now with that. We are testing of these pre-selected membranes in one-tube membrane reactor, and we are also busy with the design and construction of multi-tubular membrane reactor. Here you can see the schematics. So we want to start with the packed bed reactor to get equilibrium conversion. After that, we will cool the stream and feed it to the membrane reactor. And here you can see the 3D impression of this multi-tubular membrane reactor that we are constructing. So here is this packed bed reactor followed with the heated with the cooler, and here we have the membrane reactor that has oil around it to keep the isothermal temperature. And in this membrane reactor, we have a 7 tube-in-tube membrane. So we have here you can see the membrane, and around this annulus filled with the catalyst. We will collect. We want also to be able to measure the permeate from each of these membrane. For instance, if we want to detect if there is defect of the membrane. And with this, I finish my part, and I give word to Andrew.
Yes. Do we hear each other?
Yes, I hear.
Yes.
Okay, great. I will share my presentation.
Okay.
I hope you see it. Can you see the presentation I'm moving? Okay, I presume you see the presentation.
We don't see it.
You don't see it. No.
Okay, we'll do it again. Okay, now maybe. I think you see it now.
Yeah, now yes.
Okay, I will thank you for the word. I will be quick as possible. My name is Anže Prašnikar from National Institute of Ljubljana. So we are the permeances and the effect on the activity of prominent membranes are being further tested at our setup in Ljubljana. So the advantage of this setup is that we can perform the reaction up to 80 bar of pressure and up to 350 degrees Celsius. So this is enabled by the combination of overall high pressure design of the system with the option of pumping and vaporizing of liquid CO2 in gas feed. As was observed in the presentation, the reactor outlet lines are heated to eliminate condensation of water and methanol at high pressures. The gas pressure is reduced by orifice to allow analysis using gas chromatography. On the right side of the figure is the furnace with membrane reactor, which is shown in more detail in the next slide. So this is a scheme of a setup inside the furnace. This is with membrane module by TNO. Since we need to determine the permeances of all gases, the methanol and water is pumped into vaporizer here in the preheated flow of the feed mixture. In addition, there is a separated downstream to ensure that only gas phase enters the membrane reactor. To determine the flow rates of retentate and permeate gases, we dilute gas with helium to recalculate the flow from gas chromatography. The feed gas mixture with methanol and water can be also used to simulate equilibrium mixture as in TNO setup to efficiently use the membrane reactor. Our part is also modeling of the system. So to describe the reaction system, we first focus on membrane permeances, where we develop empirical relations for pressure and temperature dependencies of permeances. The catalyst activity is separately measured in a packed bed reactor, and microkinetic model is used. The model of the membrane reactor itself is presented in in a more detail in the next slide. The model will be validated using experimental results and then used to find operation windows which are preferred for membrane system. In this way, modeling can provide feedback information on further membrane permanences or reaction geometry improvement. The optimized conditions can be used during the operation of TNO multi-tube system, which will be also modeled. Now I will focus on the presentation of membrane reactor model itself.
5 minutes.
Yeah, thank you. So this is a scheme of a membrane module. On the right is a feed inlet. The gas enters in the outer ring of the module and passes through the catalyst layer and out on the left as a retentate. Some of the gas permeates through the membrane into the inner part of the module and exits through the permeate outlet. The mass balance equation for the retentate also includes axial dispersion in the catalyst layer since it could influence the overall activity. Flow to the membrane is now correlated with the pressure difference between membrane sites. So this is this part. The reaction rates on the catalyst surface are described in the next slide. So we develop a microkinetic model for copper, zinc, alumina catalysts, which are typical catalysts for methanol synthesis, and is based on the density function theory calculation, and it is also takes into account zinc coverage over copper, which are the active sites for methanol synthesis. Solving a large number of equations simultaneously will be performed in Ceres. So on the left, you can observe the first results of the developed model. So as a result, we obtain concentration of involved species, independence from time and axial dispersion for retentate and permeate site. The model was developed in the program Ceres, developed at NIC. There are plenty of reactor model systems available in Ceres, such as PECT, Reactor, and Batch Reactor. If anybody is interested, it's free for academic and teaching use. So to recap, we will test the most prominent membranes and model its performance. With this, I would like to thank you for your attention and the financial support from EU. Thank you.
Thank you. Please, if you have questions for both. You send by the chat. I go to open the chat, okay? There's a question from Fausto that
Yes.
Yes, it's telling you selected selective membrane with selective of 5.
Yeah, that's actually enough for we are doing also next to this experimental work. There is also evaluation of overall system system performance, and the selectivity of 5 will be good enough for conversion system, because we are hydrogen that is separated. It's combusted and used in the sorption enhanced reformer.
This another question from Richard, that is, has the microkinetic model been validated by comparison to experimental data?
Yes. The model is based on quantitative structure activity relations, and it's optimized to the experimental data.
And there is also from Fausto correction on the target required for reaction. We have target of 33% conversion. We tracked with the current performance of the membranes with the modeling work, because we are still busy with reaction tests, and based on the model we are able to achieve this conversion.
Okay.
Answer, you have a question for you as well.
So what is the sweep gas and what is the transmembrane pressure difference? So sweep gas can be used if low flow of permeate is observed, in addition to increase the concentration difference. Also, the transmembrane pressure difference can be set by retentate outlet pressure and permeate outlet pressure, and it can be between up to 75 bar in our setup.
Okay, thanks.
For us, it's 34 bar maximum.
Okay, let's thank you for the presentation and the replies. Let's move to the next presentation.
Thanks.
I think.
Hello, can you hear me?
Yes, I can see and hear you.
Okay, brilliant.
Can see your slides as well.
Can you see them? Yeah.
Yes, it's fine.
Okay,
thank you.
Brilliant. So hello everybody. My name is Adam Deacon. I'm a research scientist based at Johnson Matthey. And today with this presentation, I'm going to talk to you about some of the work Johnson Matthey has been doing in the area of MOF scale-up. So before I go into the main part of the presentation about MOF scale-up, some of you may not have heard of Johnson Matthey, so I'll briefly explain to you who Johnson Matthey is, what we do, who our customers are. I'll then talk briefly about some of our priorities in the area of MOF research, and then I'll go into the main part of the presentation and go through a scale-up case study for MOFs at JM. So Johnson Matthey is a specialties chemicals company and a world leader in sustainable technologies. Currently, our largest sector is in the area of emissions control catalysts for automotive vehicles, although we're investing heavily in the areas of battery materials and also green and blue hydrogen infrastructure and materials. Johnson Matthey has a very long 200-year history, dating back all the way to 1817, where he first started out as precious metal assayers in London. And over the years, we've kept that knowledge and that PGM chemistry, and it's still a large part of our business today. JM is also a very heavily R&D focused company, with about 12% of our employees working in research and development. And to supplement that R&D work, we also fund over 100 PhDs worldwide, looking at new technologies, new sustainable technologies. JM has many different customers in many different sectors and markets across the world, from the automotive and chemical sector to the pharmaceutical and agrochemical sector. What links all of our customers together is their need for tailored scientific solutions to the problems that they have in their respective sectors. The way that we provide those solutions is by using our 9 core capabilities. These range from characterization and chemical synthesis to product formulation and surface chemistry. And by combining all of our capabilities within JM, we can provide our customers with commercial scalable solutions to the problems that they're facing. Okay, so that was just a brief introduction into Johnson Matthey. I'll now move into the main part of the presentation, which is about metal-organic frameworks and their scale-up as well. So for those of you who don't know what metal-organic frameworks are, or MOFs are, this is just a brief introduction. MOFs are a functional hybrid material consisting of metal nodes and organic linkers. You can see here on the bottom right-hand corner, these are just some typical linkers, more common linkers used in MOFs. These are carboxylic acid-based linkers, and the metal will coordinate through these carboxylic acid groups to form these larger 3-dimensional structures with well-defined pores within the structure. MOFs are typically categorized by their very high surface areas, and about 1 gram of material can possess the same surface area as a football pitch, so they're very porous materials. MOFs are very synthetically versatile as well, so there are many different combinations of metal linkers, metal nodes and organic linkers, and the combinations can be endless. So far, there's been about 70,000 different reported structures of MOFs produced. MOFs have many different types of functionality. The first largest part of functionality is their porosity, the very porous materials. And these make them very good for gas storage applications, such as things like hydrogen and other gases. The second type of functionality is their pore structure. They have many different, the pores can be controlled. So we can change the size of these pores. This makes them very good for gas separation, such as many different CO2 separations from hydrogen or nitrogen. And finally, the final types of functionality comes from their metal nodes and organic linkers. These can be used as points for catalysis or other chemical transformations. Many people often think that MOFs are very unstable materials due to their partly organic nature. However, this is not always the case. There's been MOFs reported that can be stable under highly acidic conditions or highly basic conditions, and even to fairly high temperatures up to 400 degrees Celsius. So far, there's been lots of academic interest in MOFs for the past 30 years, and only a very few amount of products that have been on the market for using MOFs. What's really needed to make these a widely commercial material is the development of large-scale, cost-effective scale-up routes, so to make these materials commercially available. So within Johnson Matthey, we have 6 key priorities in the area of MOF research. 3 application-based priorities. These are separations and purifications, fine chemical catalysis, and finally controlled release of molecules from the MOFs. And supporting those application-based priorities, we do a lot of work in forming and scale-up of MOFs, modeling to try and identify which MOFs are the best for which application. And also we do some work in situ monitoring. These are monitoring our how these MOFs form within our reaction to better understand the reaction and help our scale-up work as well. Today, I'm just going to talk to you about our scale-up work. So when we try to scale up a MOF, there are several different considerations that we need to make, and these can be categorized into 2 categories. The chemical considerations, these are things like the concentration of our reaction, and the more concentrated, the better for us. The temperature, and in this case, we want to try and reduce the temperature. And this is especially beneficial as we're using solvents, so we want to lower the temperature as much as we can. And finally, it's the choice of solvent that we use. We have many different tools that we look at trying to choose a solvent. One of the tools that we can use is these solvent ranking tools. This was published in a green chemistry paper. This allows us to give a very quick and easy way to try and make a solvent choice for our MOF synthesis. The other type of considerations that we need to think about is physical considerations, things like mixing. Oftentimes during the MOF synthesis, the synthesis will increase in viscosity, so we need to make sure that our mixing is consistent throughout the reaction, and then we have a homogeneous mixing. Other things we need to think about is the separation and washing, and also the waste. We need to think about how much waste we're producing and what we're going to do with that waste, and try and minimize that as much as we can. And finally, we just need to think about how all these different considerations and changes we're making to the synthesis will affect the final product performance. I think there's one key area that we really need to think about when we're scaling up MOFs to make MOFs more scalable, and that is trying to reduce the amount of raw materials that we use when we are making these MOFs, especially in the case of solvent. We often use very large quantities of expensive solvent. If we can reduce that, it will really improve the synthesis. Okay, so now I'll just go through a MOF scale case study. This work was done as part of the member project, in which we look to try and scale up Nanozife 8. So Zife 8 is the structure on the side here, and it's made from organic linker called 2-methylimidazole and zinc ions. In this case, we use zinc nitrate as a source of zinc ions. It produces a very high surface area, a very porous material with a high surface area. And it also produces a material which is quite stable as well, stable up to 400 degrees Celsius. In the member project, we're using this MOF for a pre-combustion application, so the separation of hydrogen from CO2. And the reason that we need to use, we need to make nano-sized materials, nanoparticle-sized materials for this is that they will be combined, incorporated into a polymeric membrane to make a mixed matrix membrane. If the particles are too big, then they can protrude from the surface and cause defects in the surface of the membrane, allowing gas to bypass through that membrane, reducing the selectivity of that membrane. If we look at the original synthesis for Nanozife, it's a fairly simple synthesis. It's made simply from a precipitation type reaction by mixing 2-methylamidazole with zinc nitrate in methanol. And after 30 minutes, you get your precipitate, you filter it, wash it, and you have your material. However, to make nanomaterials, we need to use very dilute conditions. We need to use large quantities of methanol. Approximately 5 liters of methanol is needed just to produce 5 grams of Nanozife using this method. When we first looked at this synthesis, we tried to intensify this reaction somehow using standard methods such as increasing the concentration of the reaction or increasing the temperature, and we also play with many other parameters. However, as you can see that these parameters didn't really have an effect on the overall yield of the material. So if we increased the temperature, it didn't affect the yield. And actually, when we increased the concentration of this reaction, it actually decreased the yield that we were making. Now, this is inherently due to the chemistry that's going on within the reaction. If we increase the concentration of the reaction, not only are we going to try to increase the concentration of our desired products, we're also going to increase the concentration of our undesired products. And this is namely nitric acid. When the nitric acid is formed, the pH regime changes, and Zife is not stable under acidic conditions, so it doesn't form or redissolves into the solution. So really, there was no option for us to intensify this reaction ourselves. So we needed to find an alternative route to try and make large quantities of this Nanozife. We did find an alternative route, and that was using an alternative material, an intermediate material, which is called ZIF-L. ZIF-L is a very similar material to Nanozife. It's this structure on the side here, and it's made from the same starting materials, 2-methylamidazole and zinc nitrate again. However, ZIF-L is a less stable material. It's actually constructed from 2-dimensional layers rather than 3-dimensional in the ZIF-8. These 2-dimensional layers are held together through unreacted linker molecules. So we have unreacted 2-methylamidazole molecules between the layers of these materials. These are holding the layers together through hydrogen bonding. ZIF-L also produces very large particles, very large leaf-shaped particles, which makes it not applicable to our membrane application. And also very low porosity of only about 100 meters squared per gram versus the 1,000 or 1,500 in ZIF-8. However, we can make ZIF-L quite readily, quite easily, using a very simple synthesis. Again, kind of a simple precipitation type synthesis in water. So we mix our 2-methylamidazole and our zinc nitrate. We can do this in a very concentrated reaction and can produce ZIF-L into very high yields and nicely phase pure ZIF-L in very high yields, up to 90% yields, which is brilliant for us. Especially as we avoid the use of solvent. We can use water instead. What we can then do is we can then convert that ZIF-L into the ZIF-8. And the way we convert that ZIF-L into ZIF-8 is by refluxing it in a solvent. We can change the structure and the particle size into the ZIF-8 structure and to nanoparticle size. Now, this reaction is known in literature. However, we've managed to optimize the conditions to be able to produce ZIF-8, which is the right particle size and right phase purity with the right surface area. Now, if we compare our new route via the ZIF-L compared to our original route directly using methanol, we can see there's a vast reduction in the amount of solvent that we are using for this method, and makes this reaction much more scalable and more applicable to commercialization. So just to summarize the case study, we managed to develop a scalable route to produce Nanozife using this ZIF-L method. One of the key points is that we managed to reduce the amount of solvent that we're using by 2 orders of magnitude. This improves on not only cost, but also waste and environmental impact later on. In addition to that, we also managed to double the overall yield of our Nanozife from our original route to the new route. And we also managed to replace toxic methanol in the original route with a non-toxic solvent in our reflux route. And finally, as part of our member project, we also tried to design or tried to make an industrial scale concept of what a Nanozife plant would look like. And by taking this ZIF-L route, we think we can produce a material which is to the right specification and commercializable. All this work resulted.
5 minutes.
Yeah, thanks. All of this work resulted in a 7 times reduction in the cost to produce this material, which is incredibly beneficial to the project. So within JM, we've also looked at some other scale-up of other different MOFs as well for different projects. These are things that we've looked at the scale-up of iron BTC. We produced 15 kilograms of this MOF for another project called the Prodea project, which was looking at ammonia adsorption. And actually, we also looked at another MOF, which is nickel CPO. We managed to produce 10 kilograms of this MOF, which was used in a demonstrator unit in Egypt for heat pumps and desalination. Okay. So finally, just to kind of summarize the whole presentation, I think one of the key things that we need to think about when we are producing these MOFs at scale is reducing the raw materials, and especially the amount of solvent that we're using during this reaction. If we can do that, we can make these materials more readily available, more commercializable. The other thing is to think about is conventional scale-up methods are not always valid. So we saw the chemistry of the MOFs is also important. We saw that when we tried to intensify the original method, this was not always possible because we were producing other things, and we couldn't form these MOFs in our reaction. And finally, I just want to say that commercial large-scale synthesis as MOFs can be achieved. However, we need the right understanding. But I believe that they can be used widely. They can be widely available and widely used within our industries. So with that, I'd just like to give some nice acknowledgements. So from my colleagues in JM throughout the UK, and also one of our partners in the member project, Unizar, who helped us with some of the work that I've shown today. So thank you very much for listening, and welcome any questions that you have.
Thank you, Adam. Please add your questions in the chat.
What reactions applications are you looking at for this MOFs? In terms of the ZIF-8, we can use it for different gas separations. So in the member project, we're using it for hydrogen and CO2 separation. But ZIF-8 has been shown to be used for different applications, such as separation of different isomers of butane, butene, alkene separations. In addition to that, we have different MOFs looking at different reactions, such as fine chemical catalysis. I think the majority of our work is looking at gas separations and process gas separations specifically. Any other questions?
It looks like we don't have questions anymore, so maybe thank you, Adam, and let's move to the last presentation from Miren Echeverria.
Okay, I will share my screen. So you can see my screen on full presentation?
No, not yet. Yes, now.
Now,
Yes.
the full presentation. Yeah.
Yes.
It's okay. Yeah. Okay. Okay, so good morning, everyone. My name is Miren Echeverria, and I will present the work carried out at Tecnalia on membrane project on PBI-based mixed matrix hollow fiber membrane for pre-combustion CO2 capture. So 3 different ways are considered to reduce CO2 emission in combustion processes. They are pre-combustion CO2 capture, post-combustion CO2 capture, and oxy-fuel combustion. In pre-combustion CO2 capture, fuel gas is reacted with oxygen and steam at high temperature and pressure, and a gaseous mixture composed of mainly hydrogen and CO2 is produced. The hydrogen is commonly separated and used in a turbine to produce electricity, whereas the CO2 is captured. The use of membrane on pre-combustion CO2 capture offers several advantages. For instance, hydrogen and CO2 are already at high pressure, and as CO2 is keeping the retentate, it can be delivered already at high pressure. So the compression cost is significantly reduced. So as my colleague Oana explained in a previous presentation, among the different membrane geometries, the hollow fiber configuration is the preferred one for gas separation. And this is due to as it can be seen in this graph, due to the small diameter of the hollow fiber membranes, they can be densely packed, giving membranes modules with a really high surface area. So the ideal hollow fiber for gas separation is an asymmetric hollow fiber, and the asymmetric hollow fiber is composed of a highly porous support with a very thin and dense separating skin layer on top of the support. The separating layer is commonly situated in the outer surface of the hollow fiber membrane. So just an overlook of what is the strategy to follow to develop a membrane. It has been already explained by my colleague Oana. So the first thing we have to do is define the target performance, and based on that, we will select or develop the material. Then first, dense membranes will be prepared in order to know which are the intrinsic separation properties of the material. And if the separation properties of the material are the desired one, then so we have to check if this material can be prepared as a thin layer, both as a hollow fiber membrane or as an asymmetric flat sheet membrane. So hollow fiber are prepared, and if the target performance is reached, then we can think on scaling and prototyping. So hollow fiber membranes are usually prepared by a dry wet spinning process. In that process, a polymeric solution is extruded together with the bore fluid through a nozzle called a spinneret. So in the resident time of the fiber in the air gap, some of the solvent is evaporated and the selective layer of the fiber is formed. Then the fiber enters the coagulation bath, where the substructure of the fiber is formed, and during the spinning process, fiber is continuously collected on the drum. So Tecnalia's activities on PBI mixed matrix membrane started on M4CO2 project. So this project aims to develop a prototyping of mixed matrix membranes based on metal organic frameworks for both pre and post-combustion CO2 capture. In that project, several polymer and MOF pairs were tested in the flat sheet configuration. And in the case of pre-combustion CO2 capture, PBI was selected as polymer matrix and TIF8 as MOF filler to go to hollow fiber configuration. PBI has shown to exhibit the highest selectivity among polymer families. However, the low permeability is among the main drawback of PBI membrane. So in order to improve the permeability of the PBI membranes, TIF8 MOF particles were introduced in the polymer matrix. So with the introduction of the TIF8 particles, we are aiming to improve the permeability of the membrane. So during this project, both pure PBI and mixed matrix membranes were prepared. The membranes were first tested for single gases at different transmembrane pressure. So as you can see in these graphs, by the addition of 10% TIF8, we managed to almost double the hydrogen and CO2 permeance. The hydrogen permeance was increased for 63 GPUs and up to 107 GPUs by the addition of the MOF. For the pure PBI, hydrogen and CO2 permeance were not influenced by the feed pressure. They keep constant. And in the case of the mixed matrix membranes, the hydrogen permeance was not influenced by the feed pressure, but the CO2 permeance was slightly decreased as the feed pressure increases. And this results in a slight increase in hydrogen CO2 selectivity as the pressure increases. So a selectivity around 17 was obtained both for pure PBI and for the mixed matrix membranes. So this was for single gases, but in order to be closer to real process conditions, we also tested the membrane for mixed gases. And mixed gas experiments are represented by open symbols in the graphs. So as you can see in this slide, for pure PBI, the same performance was obtained for both single and mixed gases. However, for the mixed matrix membrane, a significant deviation from single gas experiments was observed for the mixed gas experiment. So as you can see in the first graph, the hydrogen permeance was much lower for the mixed gas experiment. It remained constant at low pressure, but then as the pressure increases, it falls to the same value as the pure PBI hollow fiber. A similar tendency was observed for the CO2. So at the beginning, it remained constant, and then it falls a bit as the pressure increases. So this phenomenon was attributed to competitive sorption between hydrogen and CO2 molecules. At high loadings of CO2, and CO2 is absorbed in the aperture of the TIF8, and therefore as CO2 concentration increases, the TIF8 nanocage gets saturated, and therefore the fast diffusion pathways of hydrogen and CO2 through the TIF8 may be hindered. The hydrogen permeance is more affected by this competitive distortion, and therefore, for the mixed gas selectivity, a lower value was obtained for the mixed matrix membrane. So in this slide, I am showing the SEM picture of both pure PBI and the mixed matrix membrane developed in N4CO2 project. During this project, in the spinning process, we were able only to increase the take-up rate up to 20 meters per minute for the pure PBI and up to 14 meters per minute for the mixed matrix membranes. And this leads to hollow fiber with quite big diameter. The diameter for the pure PBI was 307 micrometer and 470 micrometer for the mixed matrix membrane. On the other hand, the mechanical stability of this fiber was not quite good. We subject the fiber to a mandrel test. A mandrel test shows the ability of a fiber to wind and unwind in a 1/4 inch tubing without breaking. So during this test, the fiber was breaking, and these fibers do not pass this test. So in the following slides, I will talk about Membrane project. Membrane project is the continuation of N4CO2 project. And in this project, the key objective is to scale up and manufacturing of advanced materials such as membranes and solvents for 3 different prototypes. And in our case at Tecnalia, we are working on prototype A, which aims to scale up of mixed matrix hollow fiber membrane for pre-combustion CO2 capture prototype. So in this project, we are aiming to improve the scalability of PBI-based membranes. So we are aiming to increase the production rate of the spinning process and therefore decrease the fiber dimension. And we are also aiming to improve the mechanical properties of the fiber. So in the membrane project, we're starting producing PBI membranes. So we changed the PBI supplier from the previous N4CO2 projects, and also we changed the solvent used for the spinning top preparation. We changed from dimethylastamines to NMP. So at the beginning of the project, we tried to prepare some PBI membranes, but we were only able to increase the take-up rate up to 6 meters per minute, and this results in fibers with quite big diameter. So in order to increase the production rate of the hollow fiber, we decided to add polyvinyl pyrrolidone as additive in the DOP solution. And so we prepare PBI PVP blend fibers at different PBI PVP ratios, and by the addition of PVP, the as spoon fiber elasticity increases a lot. So we managed to prepare fiber at a take-up rate as high as 25 to 50 meters per minute. And as you can see, this results in a significant reduction on fiber diameter. So the thermal stability of PBI PVP blend fibers was checked, and even the thermal stability was decreased by the addition of PVP. We shown that the blend fiber are still stable up to 340 degrees C, so they are stable at typical temperatures used in pre-combustion CO2 application. And also, in order to check the proper miscibility at molecular level, differential scanning calorimetry analysis of the blend fiber was performed. The blend fiber show a single TG, which demonstrates the homogeneous miscibility at molecular level. And as you can see in the graph, the experimental TG of the blend fiber was a bit above the one predicted by the Fox equation, and this was due to the hydrogen bonds formed between the N group of PBI and the carbonyl group of the PVP. So once we proved that the blend fibers were stable, and so we prepared some pure polymer fiber with this PBI PVP blend. So a hydrogen permeance of 56 GPU was obtained for the pure polymer with a selectivity of 16.6. This performance was similar to the one obtained in the previous M4CO2 project for the pure PBI membranes. And it is worth mentioning that in the case of the PBI PVP blends, no PDMS defect healing treatment was required. As in the previous project for the pure for both membranes, the PDMS defect healing was required. So this is a quite good achievement.
5 minutes.
Okay. So then we prepared some mixed matrix membranes at 10% CIF8 loading. We managed to increase the hydrogen permeance, but selectivity was quite below the selectivity of the pure PBI, and in that case, a PDMS defect healing treatment was required to heal the defects. And so in order to decrease the number of defects of the selective layer, we decided to decrease the CIF8 concentration up to 5%. We obtain a selectivity of 17, but the permeance is below the permeance of the pure polymer fiber. So we think if we further optimize the spinning process, we will be able to increase the hydrogen permeance, keeping the selectivity constant. Regarding the mechanical stability of the fibers, this fiber successfully passed the mandrel test. As you can see in this picture, we were able to wind the fiber in the tube without breaking it. And in this last slide, I would like to compare the features of the fibers developed in previous M4CO2 project and in the actual member project. As I explained before, in the M4CO2 project, we were able only to increase the take-up rate up to 14 meters per minute, which results in fiber with quite a big outer diameter. By the addition of PVP in member project, we managed to increase the take-up rate up to 25 meters per minute, and therefore the fiber diameter was significantly reduced. By the reduction of fiber diameters, so we managed to increase, as you can see in this graph. So this is what we obtained on M4CO2 project. So for this fiber diameter, the surface area per volume ratio would be of 5,000. And by reducing the fiber diameter, we managed to almost double the surface area per volume ratio. Also, the mechanical stability of the fiber was improved by the addition of PVP, and also we make a simple estimation of the PBI quantity we would require to produce a square meter of membrane, and taking into account the PBI concentration in the dose solution, the take-up rate, and the fiber diameter. And as you can see, the PBI quantity required is half for the member project. So this is quite a good achievement. So to conclude, we demonstrate that by CIF8 incorporation into the PBI polymer matrix So the incorporation of CIF8 strongly influences gas transport, specifically in mixed gas permeation. So the improvement of fiber performance for hydrogen CO2 separation by the addition of the fillets, it's compromised at high operation feed pressure. So we observed that at low pressure, the transport through the CIF8 contributes to the permeation and to the mixed matrix performance, but at higher pressure, this contribution is reduced by strong absorption of the penetrant. And also we demonstrated that by the addition of polyvinyl pyrrolidone to the PBI, the spoon fiber elasticity increase, and this results in significant improvement in the take-up rate. So we managed to increase the take-up rate until industrially relevant values. And we prepared some PBI PVP blend membranes, which were mechanically robust and with a diameter smaller than 300 micrometer. And we also shown that blend fibers are thermally stable up to 340 degrees C. So they are stable at typical temperature of pre-combustion CO2 separation. So to conclude, I would like to acknowledge the European Union for the fundings for both membrane and for CO2 project, and of course, all of you for your attention. Thank you very much.
Thank you, Miriam. We have one question already from Anton Manakov. That is, what will be the selectivity for hydrogen and CO2 separation?
Okay, this is something we did not measure yet, but I could not answer at this moment.
Can I come in? It will be much higher than hydrogen carbon dioxide separation. So carbon monoxide is comparable with nitrogen in terms of permeation through membranes. So the permeation of carbon monoxide is very low.
Okay, any more questions? No more questions. So I'm muted, sorry. So yes, we will start. We have lunch now. We will start at 2 o'clock with the plenary session. Don't forget this. And yes, all the presenters also to put the presentation in the website of the workshop, because we need to draft the booklet. And I would like to finish and give him a thank you very much to all the presenters and the attendees for attending the session, and the presenters for presenting the speakers for presenting the activities they have been doing in their project. And see you then at 2 o'clock.